When I thought about what to say about myself, I was reminded of my first software-related job in England. I worked in the data services department, and one of my main tasks was unzipping debased databases for a school finance system. The databases would arrive in the mail on floppy disks, lots of floppy disks, CDs or zip drives. Comparing that to today, we can see how far we've come in terms of what's possible in the cloud and the sheer size of the databases we manage, making exporting to physical media somewhat impractical. We can also see how things haven't always changed. Even now, some business operations outside the scope of this talk are still powered by an AS400 mainframe. I will mention, though, that some data was still sent in the mail. Now, the hero of the talk, the hook, if you will. How do we keep systems running smoothly in places considered inhospitable to modern tech? Imagine running operations in the middle of the Sahara, deep in the heart of Saskatchewan, or high in the Rockies, remote areas with little to no reliable internet access. How do we gather and store data in these kinds of environments? Once connectivity is restored, how do we ensure the data seamlessly synchronizes with Confluent Cloud? We'll explore the architecture designed for this purpose. We're going on a journey to the edge, so it's time to pack our suitcase. This talk is based on my experiences at Ritchie Brothers Auctioneers, where they operate a network of auction sites worldwide, each with its own data and systems. When heavy equipment can't be transported to a site, a travel kit like this comes into play, allowing us to run auctions in remote locations like farms or deserts. This kit has everything you need to power an offline auction. But syncing data seamlessly with Kafka, that turned out to be a bit more challenging than just packing a few extra cables. Let's set the scene. I'll introduce the two key challenges that sent us on this journey to modernize asset management. You'll see exactly how we tackled the problems of siloed data and inefficient manual processes. Challenge 1, siloed data. At the heart of our operation was a network of auction sites, each operating in isolation. Accessing data meant logging into each site over a VPN and manually copying it to a local machine. This made coordinating cross-site activities a logistical nightmare. Our internal customers, responsible for site administration and sale days, were growing increasingly frustrated as the siloed nature of the data made it nearly impossible to get a holistic view of operations. Challenge 2. A prime example of inefficient manual processes was moving an asset between sites. It required coordinating multiple people to remove the asset from one site and then add it to another. What should have been a simple task became an arduous, time-consuming process due to the lack of centralized systems. Wouldn't it have been easier to log into one portal and handle these actions seamlessly? The problems of siloed data and manual processes were mounting, and we needed a solution. These two challenges are what drove us to find a modern, scalable solution. We were starting to see the path forwards. It was time to create a modern cloud platform that would consolidate everything into one place, reduce manual work, and allow easier data access across all sites. However, reaching feature parity and moving beyond the current systems would take time. We knew this would be a multi-year journey, so it made sense to have both the current and new platforms in sync during a phased rollout. The solution was to bridge the gap between these two platforms. We turned to Kafka and the Confluent Platform, with its schema registry for managing contracts as schemas between systems, which sets us up for success as we evolved the data requirements. We also chose to embed Debezium into our producer app to give us more control over building events from database changes. Sorry, my voice just went really weird then. Especially given the unreliable connectivity at many of our sites. The producer app would stop on any error to ensure the Postgres write-ahead log was kept until the events had been successfully processed. We built all our Kafka streams using Java and Avro schemas for the events, and hosted the Confluent Platform and the Kafka Streams apps on on-prem servers. Here's a diagram representing the asset journey, where it is routed between our cloud platform and legacy systems. The cloud platform, referred to as MARS, a handy acronym for Multi-Channel Administration and Reporting System, is the centralized point where new events are generated representing new or updated assets. The Kafka platform, which included the brokers, Zookeeper, schema registry, and K-streams, was often called Rover, after the name of the team I was a part of. A key challenge was ensuring that each legacy system processed only relevant events. We needed a way to route data selectively, ensuring that each legacy platform only processed events for sales owned by the site. This is where the event routing K-stream efficiently routes events to the correct topic. However, we had to account for the fact that each site is constrained by volatile connectivity and limited processing power. This meant that the system had to be resilient to temporary outages and capable of handling replays without overloading the site's resources. Leveraging Kafka's partitioning enhances our system's scalability. By rekeying the events and partitioning the data by sale number, we ensure the system can effectively manage increasing traffic volumes, and even as new sites are added. This approach allows each site to independently consume events without being affected by others, thereby ensuring a robust and scalable system. The asset has now reached its destination site, also known as sale site. On the consumer side, we decided to commit offsets only after the events are successfully processed and stored in the database. This strategy ensures no data loss in the case of failure. By committing only after persistence, we can reconsume messages and maintain the correct event order, ensuring consistency across the system, even during site outages. This decision did increase the end-to-end latency for events reaching a site by about a second. Now, let's break down the asset return journey, where we address performance optimization and schema evolution. In the diagram you see now, asset change events are routed back to the cloud platform. The sale site producer sends the raw CDC asset event captured from the database. The K-stream processes this raw event and transforms it into an enterprise-level asset. This approach provides two benefits. First, it reduces the load on the sale site producer, and second, it allows us to generate a more versatile enterprise asset that multiple downstream systems can consume. Decoupling the enterprise schema from the source systems has significant advantages. It allows us to enrich the enterprise asset by pulling in additional data from other topics, or adding new elements to the schema as our needs evolve. This flexibility ensures that our system can grow and adapt over time, supporting new business use cases. One of our key decisions was to use compacted topics where it made sense, particularly for enterprise topics. This ensured that if a new consumer came online, it would only receive the latest version of an event, avoiding unnecessary processing of stale events. Finally, MARS consumes the updated asset event. You may wonder why the legacy system has the pleasure of sending assets into an enterprise topic. For simplicity, I didn't add the entire flow to the diagram. Rather than explain the flow, I'll say assets in that topic could have different parts of the schema updated by MARS and sale site. They owned different pieces of the schema that changed over time as the cloud platform took over more responsibilities. So, enter stage left, our first trial by fire, operating Kafka in production. Running Kafka in production was intense for our small team. Early on, we faced an issue where our Kafka brokers kept going down, and the error messages were anything but helpful. They didn't exactly scream, "Hey, check your file descriptor limits." So we scratched our heads, sifting through documentation to figure out what was wrong. Finding solutions felt like searching for a needle in a haystack without knowing we were supposed to be looking for a needle. We often relied on community resources, forums, blog posts, and sometimes even obscure websites I remember being sent the fix on a no longer active site that mainly blogged about beer, which helped us figure out we needed to adjust our file descriptor settings. Those early months had a steep learning curve. Thankfully, since downtime wasn't as critical then, we had breathing room to experiment, but the pressure ramped up as we prepared to run Kafka in production at full scale. One particularly memorable moment was when we were troubleshooting a critical issue. It was nighttime, and I was out walking my dog while on a conference call, talking through the issue. I was trying to stay quiet because my then 6-month-old was sleeping in the next bedroom. In moments like these, you truly appreciate the complexities of managing Kafka and the lengths you go to keep everything running smoothly. After dealing with all the fires of operating Kafka, we knew we needed a better solution to overcome this adversity. In 2019, I went to the Kafka conference with a mission: to meet as many vendors as offering managed Kafka services as possible and find the right one for us. But as soon as I learned about Confluent Cloud, I knew it was exactly what we needed. Not having to operate Kafka in production lifted a huge weight off our shoulders. We had so much more time to focus on developing new features, being innovative, and delivering services that weren't even on anyone's radar, but were incredibly valuable. Of course, no transition is without its hiccups. For example, we ran into an issue with the Java timeout value for DNS lookups. The default value was set to -1 or infinity, meaning that the cache wouldn't refresh when Confluent Cloud's IP addresses changed behind the scenes. We had to adjust the setting to 30 seconds, but it's one of those little things that catch you off guard when you least expect it. We saw how the asset journey kept both systems synchronized. Now we'll automate the next step, moving assets between sites. This had previously been a manual and error-prone process. This diagram shows the 3-step process we designed to reliably and automatically move an asset between sales. First, the red arrows indicate that when a move event is triggered, the system routes a delete event to the original site, which deletes the corresponding asset from the database. Second, the green arrows show that the system waits for confirmation that the deletion was successful. This is crucial because it prevents duplication or the asset lingering in multiple places. Only after we get that confirmation does the 3rd step kick in. The blue arrows show that the add event is sent to the destination site, where the asset is added to its new home. The key takeaway? This 3-step process, delete, confirm, then add, helps us maintain data accuracy and avoid any messy overlaps. The trials, they kept on coming. Our second trial by fire came from Kafka Streams. Kafka Streams are single-threaded by default, which is great because it's easy to reason about and makes debugging simpler. That is, until you introduce a long-running processor that prevents it from responding to new events. Of course, we discovered this during the first full-blown sale we used this K-stream at. Oh, and it also happened to be the biggest sale of the year. Also, one of the biggest lessons we learned was always close your state store iterators. Rookie mistake, right? Not closing them left us confused as we tried to figure out why we had so many memory issues. Finally, after running Kafka Streams apps for a few weeks, the streams would fail with out-of-memory exceptions, and we had no immediate clue why. To get to the bottom of it, we analysed a heap dump to understand memory usage better. That's where we found the culprit, a bug in Kafka's 2.4 version. The consumer metrics weren't being closed when the consumer was released. Sometimes it's not you who introduces the issues. One of the hardest lessons we learned during our Kafka Streams journey was that things would go wrong, especially in production. It was a tough moment. We had to own the problem and be upfront with the business, explaining our mistakes, why the system wasn't responding during such a critical time, and how we planned to fix it. The most important takeaway wasn't just solving the immediate issue, but ensuring we had the right systems to prevent it from happening again. This meant diving into observability and building the tools to monitor Kafka Streams in real time. We set up more holistic logging and monitoring, especially around memory usage, so we could catch potential problems before they escalated. The experience taught us a lot about owning the challenges we faced and turning them into opportunities for improvement. We were able to use the lessons from that sale to be more resilient and fault-tolerant system going forward. We're about halfway to our destination on the road to effortless transfers. Let's see how we tackled another frustrating pain point, one of the inefficient manual processes we were determined to fix, transferring sales from one site to another or to a temporary travel kit. The old process relied on exporting all the data, zipping it up, and emailing it, and sometimes mailing it to the destination. As you can imagine, this process was slow, inefficient, and prone to errors. If the import failed, we had to start the entire process from scratch by sending a new export. We needed a solution to speed up the sale transfer process, reduce the reliance on physical exports, and automatically handle any failures. We introduced a new sale transfer flow that automates the export-import process, leveraging event routing to solve this. Over the next 6 slides, we'll see how we transfer sales between sites by exploring the sale ownership topology. For this discussion, I've used my own system to color code the elements. The blue boxes represent source and sync topics. The yellow boxes represent individual processes. Let's start by looking at how our system routes events under normal conditions. This is our standard event routing flow. Events are routed from the cloud platform to the appropriate legacy systems. On slide 2, we're starting to look at the more complex scenarios we've built on top of the event routing flow. You'll notice the addition of the green boxes. They represent state stores. These state stores are essential to how we maintain consistency and fault tolerance across the system. Now that we've recapped the normal event routing flow, let's take a look at what happens when a sale is transferred between sites in the new sale ownership flow. At the top, you see the same flow we looked at earlier. Asset events are routed based on sale number and forwarded to the right sale site. But we have 4 more steps to transfer ownership of a sale. The bottom part of the diagram shows us step 1, exporting a sale. An export event kicks off the first step of the sale transfer. This ensures that everything is set up for the subsequent events to be stored. The sale is marked as pending import, and the system prepares to hold any new events related to that sale until the transfer is complete. Next, an export success event is generated by the case stream. This event signals that the source site can now begin sending all asset events for that sale to Kafka. By confirming the export, the system ensures that the transfer is reliable, preventing any loss of data. Only after the export is confirmed do we move to the import phase. This design ensures that the transfer process is resilient to any failures. In case of issues, the events are stored safely and can be replayed, ensuring reliable transfers. Slide 3 represents the second step of the sale ownership flow, importing a sale. Now that we've started transfer ownership and stored events temporarily, we need to ensure they're properly imported by the new site. When the destination site is ready to take ownership of the sale, it sends an import event. The system then processes this event, retrieves any stored events from the state stores, and forwards them to the destination site. Once the transfer is complete, the sale status is updated, and all associated events are processed in sequence. This ensures the final parts of the journey. The new site gets all the sale data in the right order, maintaining consistency. In this slide, we're looking at step 3, where incoming asset events are checked to see if they should be routed to a new destination topic. This happens concurrently with the previous step. From the standard flow, we've made a small change. The routing processor first checks whether the event can be routed immediately. If the event doesn't require special handling, it is routed straight to the usual site. However, if the asset event is part of a sale that is waiting to be imported or has a new target site, the routing processor does something different. It forwards the event to the sale routing processor for storing or sending downstream. This multi-step process ensures that events are only routed once a sale import is confirmed, giving us a reliable, fault-tolerant mechanism for handling events in the sale ownership flow. In this final step, the sync topic validation processor checks every 6 minutes to see which integration site topics exist. This is key because new sites can be added to the system over time. Once it validates which site topics are available, it forwards the asset event to the correct topic based on the event's metadata. Here's the overview of the entire flow we just looked at. You'll notice that both the regular event routing and sale ownership flow are now in play. As events come through, depending on their status, the routing processor will decide whether they take the standard flow or go through the sale routing process for rerouted events. There's another processor that I've intentionally omitted for simplicity. It handles forcefully retaking ownership of a sale in rare scenarios when a sale was exported by mistake. While it doesn't materially affect this discussion, it adds a layer of safety to ensure sales don't vanish into the void. Our last major trial by fire is what happens when Debezium gets mad at you. Debezium is a fantastic tool, and I've enjoyed watching it evolve over the years. We were relatively early adopters, jumping in at version 0.8.2, knowing we might encounter a few rough edges. One of the more challenging issues we faced took nearly a year to diagnose and resolve. After much persistence, we tracked it down and solved the issue by upgrading to a newer version. Another issue we encountered didn't have a release ready when we first discovered it. I even created a bug ticket on my birthday according to the date. Debezium would get stuck in an infinite loop, consuming 100% of the CPU and leaving the system unresponsive. This was hard to track because the system didn't appear to be in a hung state, but it wasn't consuming events and would have to be restarted. After many frustrating moments debugging these issues, we learned a valuable lesson. Always keep Debezium up to date. I love Debezium, and it's been instrumental in our architecture. However, running an outdated version led us into many brick walls. But like with any challenge, we adapted, and after waiting for the new version, we finally got back our CPU. It's a reminder that keeping up with version updates can save you a lot of headaches. As we approach the end of our journey, there's just one last challenge to solve. Now that we have a travel kit capable of automatically taking ownership of sale and receiving all the events, we still had to figure out how to ensure this data seamlessly synchronizes with Confluent Cloud. Given that these kits can be deployed in the field for long periods, we needed a solution to ensure they could continue operating without internet access. We wanted to avoid filling up disk space with write-ahead log files, so we installed the Confluent Platform and MirrorMaker on the kits. This allowed Debezium to continue generating events locally. Here's a diagram showing how the data is synced with Confluent Cloud. When there's connectivity, the events flow from the local cluster to Confluent Cloud via MirrorMaker. And if there's no internet, no problem. The events will queue in the local cluster until we're back online. We built a custom message handler for MirrorMaker because we needed to ensure that the schema used in the local registry could be matched with the corresponding schema in the cloud registry. This was to ensure schema consistency between local and cloud environments. The handler finds the correct schema in the cloud registry, serializes the event with the appropriate schema ID, and then forwards it to Confluent Cloud. In short, the kits just work, whether online or offline. And when you're done designing and building, you step back and see this. The vast stream lineage map is taken from Confluent Cloud, and it's a great example of how complexity creeps in, even with thoughtfully and intentionally designed systems. When viewed from a high level, what started as well-defined modular pieces of a system reveals a labyrinth of topics, k-streams, producers, and consumers. This doesn't mean the system is poorly designed. Quite the opposite. It's just a reality of large-scale event streaming. You think you're building something simple and manageable, but zoom out and there's this sprawling complexity. As we near the end of this talk, I want to share a cautionary tale about something we built, the topology builder. We created it with the best of intentions, hoping to make life easier for new engineers. Kafka Streams is complex, and onboarding took forever. So we thought, why not build a wrapper with a builder syntax? It worked. It made creating streaming applications a breeze, even for those without deep Kafka knowledge. Newcomers could jump in, get things done, and add value right away. But here's where we ran into trouble. Hiding all that complexity, we made troubleshooting more challenging when things went wrong. New engineers took longer to wrap their heads around the system, which meant delays when issues popped up. It was a real eye-opener. We learned that while simplifying development is great, it's all about balancing ease of use and understanding what's under the hood. Sometimes the cost of simplifying things is losing some of that flexibility and deeper knowledge. I'll take a moment now and reflect on what we learned along the journey. Over the next 3 slides, I'll reflect on the key tools and moments that helped shape our approach. Confluent Platform stands out as a fantastic wrapper around the Kafka ecosystem. It simplified the installation and maintenance of the Kafka components. I'd also be remiss not to mention how offloading the running of Kafka to Confluent Cloud wasn't a big deal. The product has matured over the years from great to outstanding. The schema registry allowed us to reason clearly about the data being sent and received. It made the boundaries between different platforms intuitive and testable, giving us confidence to evolve the system. Finally, MirrorMaker helped us ensure seamless data replication, particularly when handling connectivity challenges or outages, giving us the fault tolerance we needed. In Reflection 2, I'll share what we learned from incidents and how they helped us improve. Each incident revealed gaps in our logging and monitoring, so it made it a priority to level up these tools. Now, when something went wrong, we could see it faster and understand precisely what was happening. We also realized that when everyone knows what's being deployed, things run smoother. There's less guessing, and people are more prepared to handle any issues that might come up. When something breaks, having a clear plan makes all the difference. We improved our communication during incidents so everyone knew what to do, who to talk to, and how to fix the problem quickly. One big takeaway was to keep our Kafka Streams apps simple and focused. Instead of trying to do too much, we kept them scoped to specific tasks, which made them easier to maintain and helped avoid unnecessary failures. In the end, every incident gave us the chance to do better. It wasn't always fun, but we came out better prepared with more reliable systems. For my third reflection, I have to bring up Debezium. Debezium came into its own as the project went on. Initially, it was a bit rough around the edges, but as we continued to work with it, we saw how it matured and stabilized, becoming an essential part of our architecture. Without Debezium, we would have struggled to capture changes from Postgres and feed them into Kafka seamlessly. It was pivotal in helping us break down silos and create a more unified view of our data across platforms. By using Debezium, we could ensure that data moved between systems in real time, helping us integrate legacy systems and new platforms in previously unimaginable ways. Just when we thought it was over, oh no, another incident. We've been creating so much great stuff. Things are going well, the team is growing fast, we're getting noticed for innovation, out-of-the-box solutions, and doing things well. The event streaming enterprise platform we dreamed of is becoming embedded in the day-to-day of operations. We've grown beyond our original scope of syncing data between the cloud and legacy platforms. Then, oh dear, something we didn't foresee. We had no idea that all those schemas we'd been deleting weren't truly deleted. After kicking off the latest prod deployments, suddenly things grind to a halt. New events cannot be produced for a critical service. Myself and another engineer stay up all night writing a series of bash scripts to hard delete the schemas we thought should already be deleted. It was a stressful, unexpected hurdle, and goes to show there's always something lurking around the corner. As one final reflection, let's look at two measurements to show the tangible results of the work we've done together. We went from moving an asset between sites taking hours to just seconds, and importing a sale, which once could take days, now happens in under 15 minutes. These numbers represent some significant wins and highlight the hard work and team effort that went into building a scalable, reliable system. Before we wrap up, let's reflect on what we've learned through this process. We've been on quite the journey together. We've seen how a small team went on a wild ride, learned a lot, and became the steward for an event streaming backbone. It wasn't always easy, but we made it work by leaning on each other through it all. There were plenty of late nights, technical hurdles, and of course the ups and downs. But through it all, we found ways to have fun, laugh at all the chaos, and support each other. That shared experience, working through the fires together, made this journey all the more satisfying. I hope sharing our story gave you a real sense of what it's like to build something at this scale, and maybe even brought a smile to your face. Thanks for being a part of this with me. Finally, the credits. I want to acknowledge that none of this would have been possible without the help of everyone in the platform team at Ritchie Brothers. Also, a special thank you to Ashley Bill, the OG rover engineer, who helps me remember some of the more esoteric details and endlessly whiteboarded with me back in the day. Thank you.